In this lesson, we need to learn about the inverse trigonometric functions. Now, you still have to remember your properties of inverse functions in general, how inverse functions work, and again, some of the properties that go along with inverse functions. If you're not clear on those things or you just don't remember them, go back and rewatch the inverse functions video first and then come back to the inverse trigonometric functions video. Alright, so we need to talk about inverse trigonometric functions. Now there's one major problem, is none of the trigonometric functions, and we have 6 of them, have inverses. Now it seems kind of crazy since we're talking about inverse trigonometric functions, but it's the case. And that's something that's going to make life a little bit difficult with this section. Now, I say they don't have inverses, and that's not completely true, in that they don't have inverses over their entire graph, because none of the trigonometric functions, if you look at all their graphs, pass the horizontal line test, which means they're not one-to-one. And remember, only one-to-one functions have inverses. So there's something we did when we were talking about inverse functions, when we said if you restrict the domain of a function enough, you can make that function a one-to-one function, and therefore it will pass the horizontal line test and it will have an inverse. And that's essentially what we have to do here with these functions, is on their entire domain none of the trigonometric functions have inverses. However, if we restrict their domain enough, we'll be able to make them have an inverse. Alright, so let's look at the sine function. We know that the sine function looks like this. Okay? It's got this 0, here's pi, here's 2 pi, this would be 3 pi halves, here would be pi halves. If I go the opposite way, this would be minus pi halves, here would be minus pi, here would be minus 3 pi halves, this would be 2 pi. Alright, so this is our sine function, y equals sine x. It's not one-to-one. Clearly, it does not pass the horizontal line test. Okay? So, what are we going to do? Well, we need to restrict the domain enough. And what we're going to do is this. If I look at this function from minus pi halves through to an x value of positive pi halves, this piece of the sine function is one-to-one, and that piece of the sine function does have an inverse. Now if I increase this piece just a little bit more, it's not going to be one-to-one anymore, because if I make this go just a little bit further, it's going to start coming back down and we're not going to pass the horizontal line test. If I increase this just a little bit further this way, we're not going to pass the horizontal line test anymore. So this is the biggest I can make this piece so that it's still one-to-one. Now I could choose a different piece somewhere along here. Like I could say, okay, how about this piece from here to here? That piece of the sine function is one-to-one as well. But to be consistent, we look at the same piece all the time. So what we're going to think of is we're basically cutting our sine function here and here, and only looking at it inside this window. And inside this window, the sine function is one-to-one. So if the sine function is one-to-one in that window, that piece of the sine function from here to here will have an inverse. Now that causes some issues down the line of, okay, well, we're not looking at the entire domain, so how does that affect the inverse function? Well, we'll talk about that in a second. First of all, if this function does have an inverse, how are we going to notate it? Well, there's 2 ways to notate it. This is y equals the inverse sine of x, and that we put that little -1 up there. It looks like an exponent, but it's not an exponent. It's the same notation, this little -1 here, that we use for inverses in general when we wrote f inverse of x. Okay, so that's one method of notating it. Another method of notating is this arc sine of x. We write an arc, the word arc, in front of the sine function, and that means inverse sine. Each notation is used commonly. You should be familiar with both. This notation here has some issues. The issues it has is that if I wanted to square the sine function, I would write it like this. Right, that's the same thing as the sine of x all squared, and we've talked about that. So if I do this, put the little -1 there, it could be confused with an exponent, even though it's not an exponent. This -1 is purely an inverse notation. So that could cause an issue. So in order for that to not be an issue, that's why we can change the notation completely to the arc sine notation. The only thing I could tell you is that if you ever see a -1 there, it will never be an exponent, and it will always represent the inverse. Any other number that I put here, like a 2 or 3 or a -5, it will always represent a power. So just something to keep in mind. It is a little tricky, but that's one issue with this notation here. So the arc notation is used as well. But you need to be familiar with both. Your textbook uses both. Most textbooks use both notations. All right. So now we got to look at this idea of the domain restriction, and then that also affects the range. So what we did is we restricted the domain of the sine function. Okay, so if we're looking at this sine function here, we restricted the domain, the x values, to be between -π/2 and +π/2. Those are the x values I'm using here. The y values in there are still between +1 and -1, and I get every y value in between because my graph goes from here up to here. In that case, it has a y value of 1 and a y value of -1. So the y values for this function, I can do a little bit of erasing here, the y values for this function are going to be between -1 and 1. Now that's for the sine function. Now what we need to do is realize, how does that affect the inverse sine function? So what happens is this. Remember we had this picture, this idea of what a function does, right? Here's my function. My function is y equals sine x. And that takes me from here to here. The x's I'm going to start with, remember, are restricted between -π/2 and +π/2. And this is my domain. Okay? Now the y values I get, the range values, are going to be between -1 and 1. So if I plugged in π/3, okay, what would that get matched up to? Well, I say, okay, π/3 will get matched up to what? Well, the sine of π/3 is square root of 3/2. Okay, so that goes there. So this value π/3 is between -π/2 and +π/2, and then goes to a y value that's between -1 and 1. All right, how about another one? I'll say, I don't know, π/4. π/4 is going to get matched up to square root of 2/2. Same deal. This is my x value. These are my y values. Now remember your inverse. Your inverse goes the opposite way. So my inverse is going to go this way. Okay. And the function that goes that way is this function y equals the arc sine of x, or the inverse sine of x. Now, this is my domain for my inverse, and this is my range for my inverse. And one thing that happens when it comes to inverse functions is that the domain and range for the original function are flip-flopped in the inverse. So in this case, the domain is my x values are between -1 and 1, and my y values are going to be between -π/2 and +π/2. Okay. So this domain and range restriction for the original function to make an inverse exist is going to affect the inverse domain and range. Okay? Because the domain and range of an inverse are the reverse of the original functions. Now, again, what does that mean really for you? Well, the idea is when it comes to domain, these are the things that I can plug into the function, and these are the things that come out of the function. These are the answers I'm going to get for an arc sine function. The only answer I'll ever get is an answer between -π/2 and +π/2. And this is a problem, because you're going to have a question like this. Find the arc sine of square root of 2 over 2. In that case, I'm going to plug square root of 2 over 2 into the arc sine function and figure out where it goes. Well, clearly from my picture you see it goes back to pi fourths. And the way you're going to answer that question, if you don't have this nice picture sitting in front of you, is you're going to say the sine of what function equals square root of 2 over 2. I mean, that's basically it. You're trying to find the angle that when I took the sine of it, I got square root of 2 over 2. In this case, the answer is pi fourths. That's how arc sine work. It's the reverse of the sine function, essentially. Instead of plugging an angle into the sine function and getting a y-coordinate, we have a y-coordinate we're starting with, and we're trying to figure out what angle gave us that y-coordinate. Now, there's the problem. Think about your unit circle. Here's pi over 4. Okay. The y-coordinate there is square root of 2 over 2. What about this angle over here? The y-coordinate here is also square root of 2 over 2. That would be 3 pi over 4. So how come when I take the arc sine of square root of 2 over 2, I get pi over 4 and not 3 pi over 4? Because technically, this question that says what angle when I take the sine of it gives me square root of 2 over 2 could be answered with both of these. And the issue comes right here with this. The only answers I can get out of an arc sine, in this case we got pi fourths, are answers between minus pi over 2 and positive pi over 2. 3 pi over 4 as a number is not in this range. So if you want to look at what kind of answers we can get out of an arc sine, let me clean this up. You have to look at your circle. Here's your x, here's your y. This angle right here would be 0. 0 is right between these two angles. I go from 0 to pi over 2, I go a quarter turn that way. Here's pi over 2. I go from 0 to negative pi over 2, I go a quarter turn that way. The answers I'm going to get out of an arc sine have to fit in this quarter turn in each direction setup. If they don't fit that quarter turn in each direction setup, then they're not an answer I can have. So 3 pi over 4 was over here. 3 pi over 4 is not within a quarter turn clockwise or counterclockwise of the x-axis, positive x-axis. So that's why 3 pi over 4 will not be an answer. And as long as you stick to these restrictions, then it's not too bad. But you got to remember the restrictions. Let me give you another one. Find the arc sine or the inverse sine of negative 1/2. Okay? So I gotta say, basically what I have to ask myself is the sine of some angle theta equals negative 1/2. What's that angle? That's the answer to this question. Well, negative 1/2. Okay, I can try and start drawing a little picture here. So I start to think about, alright, here's my xy plane, negative 1/2. I could have negative 1/2 in two places. I could have a negative y coordinate here or a negative y coordinate here. Automatically this one's out because it's not in that quarter turn in each direction. So I gotta think, okay, the y coordinate is negative 1/2. And if I remember back to my unit circle, which y coordinate would that be? Well, there's two possibilities. This angle right here, which is 11 pi 6, or this angle here, which is minus pi 6. They both end up in the same spot, and both will give me the negative 1/2, but this one right here is no good, because that's more than a quarter turn in either direction. However, this one, which is less than a quarter turn in the clockwise direction, fits my criteria of being between minus pi halves and positive pi halves. So the answer to this question, the inverse sine of negative 1/2, is going to be negative pi over 6. Even though 11 pi over 6 will get me to that same location, and the sine of 11 pi 6 is negative 1/2, minus pi 6 is the only answer I can give because that's the only one that's between negative pi over 2 and positive pi over 2. Once you get this idea down of I have to stick to these restrictions, the inverse functions from there are not too bad. They're just working backwards. Essentially what you have is, you have your unit circle. You're starting with your points on the outside, either x or y coordinates, and you're going back to figure out what angle gave you that y coordinate or what angle gave you that x coordinate. You're just reading the unit circle backwards instead of forwards. And if you have your unit circle down, then this is no issue. But you got to keep track of these restrictions. Okay? The domains are also a problem. Right? We know that the sine function in general has a domain of all real numbers, but the arcsine function does not. The arcsine function has only the domain to be -1 to 1. So that means the only things I can plug into the arcsine are -1 to 1. So if I wanted to do, say, find the arcsine of 5, I can't do it. It's undefined. I can't do it because 5 is not in my domain. Which, you're not going to see a whole lot of that or really any of it, but it's just something to keep in mind. More or less, you're going to be focusing so much on the range, the answers you're going to get out of the arcsine, but every once in a while, you still got to remember what the domain for the arcsine is. What can I plug into the arcsine function? I can only plug -1 to 1 into the arcsine function, so this can't happen. But -1/2 can, okay? Square root of 3 over 2 can, square root of 2 over 2 can, 1, 0, all those can, but not something like 5. Okay, so now let's look at the cosine. So if I looked at the graph of y equals cosine x, okay, we know that that graph looks like this. Here's 0, here's pi over 2, here's pi, here's 3 pi over 2, here's 2 pi. And my graph's not always that great, but it gets the point across, hopefully. So here's some of my angles. Now the problem is I can't look at it in the same way I was looking at sine, because if I look at it from minus pi halves to positive pi halves, it's not 1 to 1 there. Okay, it doesn't pass the horizontal line test, so that's out. So I got to look at it in a different location. Well, here's what I'm going to do. I'm going to look at it from 0 to pi. And if I look at it from 0 to pi in sort of this window here, where max is here at 1, min's down here at -1, this piece of the sine function, or cosine function I should say, is 1 to 1. So if I look at the x values between 0 and pi, I'll be working with the y values between -1 and 1, and these will be my restrictions. As long as I stick to these restrictions for the cosine function, it will be 1 to 1 and will have an inverse. What will the inverse be? Well, the inverse will be y equals the inverse cosine of x, or arc cosine of x. The domain for this function will be x values have to be between 0 or -1 and 1, and the y values have to be between 0 and pi, because it's the reverse of these. So these are the things I can plug into the inverse function, and these are the answers I'm going to get out. So when we think about the sine function, it was a quarter turn in each direction was what we could use for the arcsine, right? That's not the case for cosine. Cosine's 0 to pi. Cosine can only go counterclockwise and only go a half a turn clockwise, because here's 0, here's pi. I can't go this way at all to get my function, and I can't go more than half a turn counterclockwise to get my answers. So if I stick to those restrictions, then I can do my inverse cosine. Let's go one more. Let's go tangent. So if I say, okay, let's go y equals tan x, what's the graph look like? Well, the graph looks like this, right? It's got an asymptote here and here. This would be at pi halves, this would be at minus pi halves. Then I have another one of these, and another asymptote, another one of these, and another asymptote. And this is not a one-to-one function. However, if I look at it between these two asymptotes, this function is one-to-one, does pass the horizontal line test. So that's the piece I'm going to look at. So if I restrict my domain for my tan to be x between, here's an issue, but x between minus pi over 2 and positive pi over 2, and then my y values in that interval. Oh, there's another issue here. Hold on. I'll talk about these or equal to's in a second. The y values in this interval go from negative infinity up to positive infinity. This would be my restrictions for the tangent function. Flip them around. Those are restrictions for your inverse tangent function, notated the same way as the other two. Now notice I didn't put the or equal to sign here. There's no or equal to sign here or here. Now there's a reason. Because this function isn't defined at those places. So that's where the vertical asymptotes are. So they're not in the domain of the tan in the first place. So then I can't include them in the domain when I reverse it and go to the arctan. So that's why there's no or equal to here. Same thing with the negative infinity to positive infinity. You can never have an or equal to when it goes to positive and negative infinity, because infinity is this growing value. It's constantly moving. And if that's the case, then you can never reach it and you can never be equal to it. So you're never going to have an or equal to with an infinity anyway. But nonetheless, this is my domain and range restrictions for the arctan. So what you're going to have to make yourself familiar with is this little table. This table lays out what the domain and ranges are for the different inverse trigonometric functions. I only showed you the first three, sine, cosine, tangent, because those are the most common. But really the other three can be done much the same way. You're going to cut those functions up. You're going to restrict their domains. That's going to restrict their ranges. You're going to flip the domain and range around, and then you're going to have the domain for the arcsine, arccosine, arctangent, arccotangent, arcsecant, and arccosecant. So these are the domain and ranges that you're going to have to familiarize yourself with. Okay? These are the things that I can plug into these inverse functions, and these are the answers that will come out. And the nice thing is it's not a whole bunch of different ones. They're either pi over 2 and minus pi over 2, right? Or they're 0 and pi. So it's really two different categories. Which ones fit into the minus pi over 2 to positive pi over 2? Some of them don't have the or equal to, but still it's minus pi over 2 to positive pi over 2. And some of them are the 0 to pi. So it's two basic ranges you got to remember. Alright, so what you're going to have to get used to right now, at first with these inverses, you're going to have to be able to evaluate an inverse trigonometric function. So here's a couple of examples. Find the arc cosine of square root of 2 over 2. So if I'm going to do this, the first thing I'm going to say to myself is, can I do it? Is square root of 2 over 2 in the domain of the arc cosine? Well, is it between negative 1 and 1? And the answer is yes. Square root of 2 over 2 is between negative 1 and 1. If you're not sure, if you don't know, you could always just plug it in your calculator, look at the decimal, and you'll be sure it is. But I think all of you should know that square root of 2 is smaller than 2. And if you take a value that's smaller than a number, put it in the numerator, the bigger number in the denominator, you would have a number smaller than 1. Alright, so now what's the answer? Well, the answer is going to be some angle. And the way I come up with that angle is I got to say, really ask, the cosine of some angle gives me square root of 2 over 2. What angle would that be? Well, if you look at your unit circle, pi fourths. Right? Pi fourths would be that angle for which the x coordinate is square root of 2 over 2. So this angle is pi fourths. There are other angles that also would give me square root of 2 over 2. There's another angle down here. That could be minus pi fourths. If I look at it this way, it could be, what would it be, 7 pi fourths. But those are no good. Those can't be used because I gotta be between 0 and pi. 0 to pi is a half a turn this way. The only angle that fits that would be pi fourths. So pi fourths is my answer. It's going to take you some practice to get this down. But this is what we've been practicing since we started regular trigonometric functions. It's remembering your unit circle. All right, let's do another one. The inverse cosine of -1. So again, can I do it? Yes, it's in the domain. The answers I'm going to get out are between 0 and pi. What angle would it be that gets me this answer of -1? Well, right away, if you remember, this angle right here, the x coordinate is -1. That angle is pi, so the answer is pi. And that's fine because pi is in my range. Okay, let's keep going. Arctan. What's the arctan of 0? Now these are a little bit trickier because you have to do y divided by x to get this answer. This is not just a y coordinate or an x coordinate. So I got to think about, okay, well, what angle is this going to be? Well, I look at my circle, zeros and ones. Those are just these angles that fall here are the only ones that'll work. So this is 1, 0, this is 0, 1, this is -1, 0, this is 0, -1. Which one of these, if I divided the y by the x, because that's how I do tangent, y divided by the x, would I get 0? Well, these two, okay? Y divided by x would get me 0. So that means the tan of one of those angles would be 0. So this angle could be 0 or 2 pi. This angle could be pi. Which one of these can I use? Arctan. The answers have to be between -pi over 2 and +pi over 2. Well, that's too big. That's too big. So my answer would be 0. One more. The inverse tangent of -1. Alright, what angle is that going to be? If I move my way around the unit circle, when I divide all my x's and my y's, I got to get -1. Well, think about this answer right here. This angle is 3 pi fourths. Square root of 2 over 2, negative square root of 2 over 2. If I divide those two things, I'll get -1. Is 3 pi fourths an answer I can put here for theta? Is it in this range? The answer is no. So that's out. But this angle right here, which has square root of 2 over 2, and sorry, if I go back to 3 pi fourths, the x is negative, the y is positive. It's a small mistake on my part, but still you get -1, and that's still not an option. Alright, so we go back to this one. Square root of 2 over 2, negative square root of 2 over 2 is the point. Divide those, I would get -1. This is minus pi fourths. That is an answer I could give. So then the theta here would be minus pi over 4. Okay. Okay, so now that you're accustomed to evaluating inverse trigonometric functions, another thing we need to talk about is the composition of these inverse trigonometric functions. And what you're going to have to do is remember how compositions of functions in general work. Remember, this is what a composition looks like when I take one function and plug it into another. So if I do the composition of two functions and they happen to be the inverse of one another, there was something that we talked about with inverse functions, and that is we think like they cancel each other out and all you get is x. Same thing if you do it the other way, and the order doesn't matter. When you take the composition, plug one into the other, we think of them like they would cancel each other out. And it's not direct canceling, but that's sort of this property, is that all you're left with is an x. So the sine and the inverse sine are the inverse. So if I look at something like this, the sine and the inverse sine are the inverse of one another. So if they are the inverse of one another, when I plug one into the other, we would think of it almost as if like these two cancel and I'm just left with the x. And if I do it the other way too, sort of the same idea here. Think of like these things cancel and I'm just left with whatever's inside. In this case it happens to be y. Now there's one small catch to all this, and the small catch to all this is we have these domain and range restrictions. And that is, alright, when I look at the domain for inverse sine, the domain is -1 to 1. So if this is the case, if this is the one I'm looking at here, okay, what I would do is I would take the inverse sine of x first. Whatever answer I get, I would then take the sine of that. So if I'm doing the inverse sine first, I got to think about what can I plug into the inverse sine. Well, what I can plug into the inverse sine here for x is x is between -1 and 1, because that's the domain. So as long as I can plug x in here and do this part, then essentially I should be able to then do the second piece, and if that's the case, both of these pieces should cancel out and should just give me x. If I look at this other one here, the inverse is on the outside. So I would take the sine of y first. So whatever y is, I plug y in there. I take the sine of y first. And for sine by itself, the domain is all real numbers. So that y technically could be any y. However, then whatever I get for this piece here, I'm going to take the inverse sine of it. If I'm going to take the inverse sine of that piece, this is the answer that's going to come out after that. Well, the only answers that'll come out after an inverse sine are answers, or y's in this case, between -pi/2 and +pi/2. So if I do this composition, or the other order, okay, technically I could think like these two cancel and I'll just be left with x, or these two cancel, I'll just left with y, as long as I follow these possible restrictions, because these are the restrictions for either domain or range for my inverse functions. And I think there's a real easy way to remember this. The real easy way to remember this, if I erase some of this for you, is if your inverse is on the inside, you got to think about the domain for that inverse. If my inverse is on the outside, I got to think about the range for that inverse. And as long as I follow those things, the domain for the inside or the range for the outside, then I can simply just cancel. Now I'm going to give you some examples. We're going to see some other things that could come up here, but generally all these other ones we're looking at, I have cosine, I have tangent, and really you could do the other three as well. I just wrote 3 of them down here. It's the same deal. Cosine's on the inside. The domain for inverse cosine is -1 to 1. Inverse cosine's on the outside. The range for inverse cosine is 0 to pi. Inverse tangent is on the inside. The domain for inverse tangent is all real numbers. Okay. However, when the inverse tangent's on the outside, the range for inverse tangent is -pi/2 to +pi/2. Again, I could do the same thing for the other ones. These are the most common, so that's why I only give you these, but really we could look at them for the others as well. It's not just some random value of x is the key. These properties do not apply to arbitrary values of x. They are specific values that you need to worry about in order to apply these particular properties. Okay, so here's some examples. You'll see kind of what I'm dealing with here with these properties. All right, so let's look at the first one. The tan of the arctan of -5. What I would like to do would be to say, okay, cancel these two since they're the inverse, and the answer is -5. Whatever's inside here, that's my answer. Now that's only possible if I follow these restrictions. All right, so what are we looking at? Arctan's on the inside. If my inverse tangent's on the inside, I got to worry about the domain for the inverse tangent. Well, the domain for the inverse tangent is all real numbers. So as long as this value right here is any real number, which basically means anything, then I can use the property of cancel, cancel, answer is -5. And that's it. That one's very simple. But that's not always going to be the case. It's not always going to be that simple. Let's go to this next one. The arc sine of the sine of 5 pi 6. So, arc sine's on the outside. Inverse sine's on the outside. I got to worry about range. Well, 5 pi 6, is that in the range? Is that between negative pi over 2 and positive pi over 2? And the answer is no. Because if you look at your graph of your unit circle, and we're always just going back to the unit circle, 5 pi 6 is over here. Okay. 0 to pi halves, 0 to minus pi halves is here. I'm not in those quarter turns, so this is not in this range, so I can't simply apply the property and say cancel, cancel, answers 5 pi 6. We can't do that. Okay? So what are we going to do? Well, you could just say, well, problem can't be done, move on, but that's not what you're going to do. What you're going to have to do is look at this a slightly different way. It's not as easy as this first one. So what I'm going to do is take this one in steps. I'm going to say, okay, what would I do? I should work with inside the parentheses first. So the first thing I'm going to do is find the sine of 5 pi 6. Okay. Well, the sine of 5 pi 6. Here's 5 pi 6. I got to think about what's that y coordinate there. Well, that y coordinate is going to be a half. So if the y coordinate's a half, then the answer is sine of 5 pi 6 is a half. Okay. Now, the second thing I'm going to do is I'm going to find the arc sine of the sine of 5 pi 6. Well, the sine of 5 pi 6 is a half. So really the arc sine of a half. Well, how am I going to do that? Well, do it like we've been doing previously. I got to ask myself the sine of what angle gives me a half. And 5 pi 6 is one of them. But remember, 5 pi 6 is not the kind of answer I can get from arc sine. I need to get the angle that's over here, which would be pi 6. That would also have a y coordinate of a half. Okay. So here I'm going to say the arc sine of a half is pi 6. And that's the answer for the whole thing. So what's going to happen is sometimes this answer right here will not simply be the answer because you can't cancel. But the answer you're going to get would be some multiple of that. The multiple that fits the range restrictions that you're looking for. Alright, let's do another one. The cosine of the inverse cosine of pi. So inverse cosine's on the inside. When your inverse is on the inside, you got to worry about domain. This is the domain for the inverse cosine. Pi is not between -1 and 1. So I can't just say cancel, cancel. The answer is pi. It's not going to work. So what am I going to do? Well, I could try and do it the same way I did the last one, but there's an issue. Because the way I did the last one is I said, let's do what's inside the parentheses first. So I say, okay, what's the inverse cosine of pi? The problem is, I can't do that. Pi is not in the domain for the inverse cosine, which means I cannot find the inverse cosine of pi. So if this can't be done, if this is undefined, then the whole thing can't be done. So the cosine of the inverse cosine of pi is undefined. So there's some cases, if you just review, some cases where it's simply just cancel, cancel, there's your answer. Some cases where you can't cancel and cancel, like this arc sine one, but you still can come up with an answer. And some cases where you still can't do cancel, cancel, and this is your answer. And there's no other way to do it either, and the answer is just undefined. Alright. Here's one more set of examples. Now the deal with these examples is they have inverse trigonometric functions and trigonometric functions and compositions, but they're not the inverse of one another. In this case, there is no fast way to get through these. You have to slowly do them piece by piece. First one, the sine of the arctan of 0. Since sine and arctan are not the inverse of one another at all, there is no way I could say, let's cancel this, and the answer is 0. So what I'm going to do is, step by step, like I did with the one on the last section. I'm going to say, first thing I'm going to find is the arctan of 0. Okay. What's the arctan of 0? Well, the arctan of 0 is 0. Because if I was to take the tan of 0, I would get 0. And that's one we've done previously. Then the second thing I'm going to do is find the sine of the arctan of 0, which is the same thing as saying the sine of 0, because the arctan of 0 is 0. Well, what's the sine of 0? Well, think about 0, 0 degrees, 0 radians. What's the y-coordinate? And the y-coordinate is 0. So this whole thing's answer is just 0. Now, it looks like I did just go cancel. The answer's right there, but that's coincidence. All right. Let's do this next one. The arcsine of the cosine of pi sixth. So first thing I'm going to do is find the cosine of pi sixth. So you got to say, all right, cosine of pi sixth. This is old stuff. Cosine, x-coordinate. Look at your unit circle. What's the x-coordinate for pi sixth? Square root of 3 over 2. Okay. Now that I have that, the second thing I'm going to do is find the arcsine of the cosine of pi sixth. Well, what am I going to do? The arcsine of square root of 3 over 2. The arcsine of square root of 3 over 2 is going to give me pi thirds. Why? Because if I look at pi thirds, the y-coordinate for pi thirds is square root of 3 over 2. So the sine of pi thirds is square root of 3 over 2. Therefore, the arcsine of square root of 3 over 2 goes back to pi thirds. So this thing is pi thirds as a whole. Okay. All right, one more. So let's do this one. The tan of the inverse secant of square root of 2. Alright, so what are we going to do? First, what's the inverse secant of square root of 2? Now this one's going to be tricky because you're probably not as good at your inverse secants as maybe your inverse cosines, which is fine. We can do this in terms of inverse cosine. Alright, so let's get some room here. I'm going to delete some of this old stuff. So, with all this, it's always nice to draw some pictures sometimes. So, right, inverse secant. So if I'm doing the inverse secant of square root of 2. Okay. The answer for this is some angle. And essentially the idea is the secant of some angle gives me square root of 2. But secant and cosine are the reciprocal of one another. Well, that question is the same thing saying the cosine of some angle equals 1 over the square root of 2. Well, that might not look too familiar to you either, but let me do something else. Let's take the square root of 2 and rationalize it. So I get the square root of 2 over 2. Now that should look very familiar to you. What angle, when I take the cosine of it, do I get square root of 2 over 2? And you should be thinking right away, pi fourths. So if the cosine of pi fourths equals square root of 2 over 2, then the secant of pi fourths should be the reciprocal, which is just square root of 2. And therefore this is pi fourths. Alright, so the first question is, what's the inverse secant of square root of 2? And the answer is pi fourths. Second question, what's the tan of the inverse secant of square root of 2? Which is the same thing as saying, what's the tan of pi fourths? And you should be able to do that. Take the y and the x coordinate, divide them. They're both square root of 2 over 2 for pi fourths, so I get 1. So this whole thing is equal to 1. I think when you come across these inverse secants, inverse cosecants, inverse cotangents, it's much easier to look at them in terms of their reciprocal functions, because I think you're going to become more familiar with sine, cosine, and tangent than the other three. If that's the case, think of it this way. If the secant of theta equals something, the cosine of that same angle equals the reciprocal of that something. And then go from there. So you now are familiar with inverse trigonometric functions, how to evaluate inverse trigonometric functions, and this concept of the composition with these inverse trigonometric functions. And largely all it is doing the same thing we've been doing, just kind of going backwards with it.